Hello, everyone. Welcome to the October 2025 Link Tech Talk. My name is Colin Ryan Chandler, and our co-host is Mi Dai. We are both LINCC Frameworks project scientists. I'm at the Dweck Institute at the University of Washington, and Mi is at the University of Pittsburgh. Link Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. And unlike traditional talks you might hear at a conference, Tech Talks highlight the technical aspects of the work being done, and we hope these talks provide a useful forum for a range of groups and authors to present and to learn about and discuss efforts of interest in the analysis of LSST data. LSST texts are delivered virtually every second Thursday of the month at 10 a.m. Pacific. And let's see, so today our speaker is Charlotte Ward, an assistant professor at Penn State's Department of Astronomy and Astrophysics. Charlotte's group specializes in AI/ML applications to wide field survey science, especially relevant for LSST, and with focuses including cosmology and time domain science, such as active galactic nuclei or AGN. And today Charlotte's going to be telling us about Scarlet2, a multi-resolution forward modeling framework for joint analysis of imaging data from Rubin and complementary surveys. This project was awarded a LINCC Incubator grant, which you can learn more about at the LSST Discovery Alliance website, lsstdiscoveryalliance.org. For the talk, ask questions in Zoom or in the hashtag link-tech-talks channel on the Discovery Alliance Slack. And on Zoom, you can type questions into chat or raise your hands. And as a friendly reminder, these talks are being recorded and they will be posted on YouTube channel. And so with that, Charlotte, please take it away.
All right, thanks, Colin. So today I'm hoping to give an overview of Scarlet2, which is a multi-resolution forward modeling code that we're primarily aiming to use with Rubin, but also with complementary surveys such as Euclid and LS4. And this code originally started working with a team at Princeton. So Peter Melchior sort of runs the development of Scarlet2. Benjamin Remy is another postdoc who has been at Princeton working on this. And then over the past few months, we've been really lucky to work with a LINCC Incubator team, Max West, Drew Oldag, and Sean McGuire, who have really helped us make this software much more accessible and usable for the wider community through a number of features, which we'll chat about today. So my plan for this presentation is to first talk about the motivations for building Scarlet2, a brief overview of some of the science applications, and then a bit of an explanation about how it works. And I'm hoping this will set the scene for us to understand why we needed the LINCC team to really help us make this very complex software more easily usable to users who want to come in and use it for their own observations and their own science case. So the surveys that we've really focused on using Scarlet2 on are, of course, Rubin, which will provide us with these really deep and multi-epoch imaging over the next 10 years with pretty high resolution and will allow us to do a lot of time domain science with Scarlet2. But one of the things we really want to do with Scarlet2 is use it to simultaneously model observations from multiple surveys at once. And one of the big ones for this is Euclid, which is a space-based survey that will survey many fields in common with Rubin at very high resolution in the infrared and the optical. Another survey that we hope to model within this framework, in addition to Rubin and Euclid, is LS4, the C.S. Schmidt Southern Survey, which will be shadowing Rubin fields and providing high cadence photometry of transients in the regime where Rubin saturates, allowing us to combine photometry from Rubin and LS4, as well as Euclid imaging of host galaxies, so that we can get the most information possible across the widest range of magnitudes possible. So the motivations for building Scarlet2 to jointly analyze data from surveys such as Rubin, Euclid, and LS4 was firstly for cosmology. So we really want to be able to combine the wavelength information across Euclid and Rubin, for example, in order to get accurate photometric redshifts by getting very broad SEDs of galaxies. And we also want to get really accurate galaxy morphologies for things like lensing. And we can do this by combining the high resolution of Euclid with the depths of Rubin, as well as their wavelength coverage, in order to produce the best galaxy catalogs possible for various cosmological analyses. And one of the things that Scarlet2 has been built to address is the deblending challenge. So once we get to the depths of Rubin, and these plots are kind of showing as we go from SDSS to decals down to Rubin-like depths in this HSC image, we start to have these additional challenges where around half of galaxies are overlapping with other galaxies, so that 15% of sources have unrecognized blending with faint background sources. And this then has knock-on effects, and the galaxy photometry can be inaccurate, which is really important for these cosmology applications. So this is why that we really want to be able to model these deep Rubin images with additional images from Euclid, where the higher space-based resolution allows us to see where galaxies are overlapping in crowded fields and make sure that we get accurate flux measurements and morphology measurements using the data from both surveys. And as I mentioned, we want to get this broad wavelength coverage. So having joint pixel processing from multiple surveys allows us to get the best extraction of SEDs across Rubin's optical bands shown here, as well as Euclid's infrared bands. And this is, of course, useful for photoz's. And we also want to do time domain science across the different surveys. We want to get optical and infrared light curves across Euclid, Rubin, and LS4 for science cases like identifying dust reddening in supernovae, for looking for dust echoes from tidal disruption events and other nuclear transients, and looking for things like self-lensing flares from SMBH binaries, which have a strong wavelength dependence. And another advantage of combining the photometry across multiple surveys without worrying about reference image mismatch is that you can get long multi-survey baselines for AGN. And then once we're going to sort of decades of survey data across different surveys, that can be really useful for things like SMBH binary searches and studies of AGN variability. Another aspect where it really helps to be able to jointly model high resolution data with low resolution multi-epoch data is to identify whether transients are within galaxy nuclei or offset from their galaxy nuclei. A large fraction of transients in extragalactic fields are supernovae, and a smaller fraction of them are nuclear transients like tidal disruption events. And early identification of what they might be so that we can get good, quick spectroscopic follow-up can really depend on identifying whether a transient is nuclear or not. So by jointly modeling high-resolution space-based data with lower-resolution multi-epoch data, this can help us to identify if transients are offset. And then we can also do things like look for unusual wandering transients from black holes, for example, and sort of rare objects where we really need to characterize the offset between a host galaxy and a transient. And then finally, it's really important to have good host galaxy characterization for transients. We want to understand the SEDs and morphologies of transient host galaxies to answer a number of science questions. Some examples include whether tidal disruption events prefer post-merger systems, why they're in the green valley of galaxies. We want to understand the metallicity of supernova hosts. We want to understand the preferences for transients like superluminous supernovae and what kind of environments they live in. So there are a number of different investigations in various fields within time domain astronomy where we want to be able to have good identification of host galaxies and their properties. So all of these motivations, whether it's getting good galaxy catalogs with good photometric redshifts and morphologies for cosmology, or whether it's understanding transients in their environment, all benefit from having a framework where you can model imaging from space-based surveys and ground-based surveys simultaneously. And this is a plot from Dustin Lang, who developed the tractor, a precursor to Scarlet2, which explains this really nicely. The way that we can do this forward modeling approach is by having models of our observations. So we understand our individual observations, we understand what their point spread function is, what their depth is, what their pixel scale is, what their astrometric solution is. And we might have a set of observations from different surveys that have very different, point spread functions and whatnot. But each one of them we can model. We put this information into our forward modeling framework. And then we have a model of the sources in the sky. We know where the galaxies are, what their colors are, what their shapes are. And then once you've characterized both your observations and their properties, as well as the sources that you wish to model, you can then do this forward modeling where you take your observation, you take your internal model, you render it to look like each observation, and then you can fit for your model in pixel space by making it look like your observation. And with this approach, you can simultaneously model images from different surveys while improving your internal model of the galaxies and transients in the images. So just to give some context about what the code has to do for this multi-survey modeling. So here, for example, we have a particular image, and that's on a pixel grid. And then we want to model it simultaneously with a different image. That image might have a relative rotation, for example, so we need to be able to resample between these rotations. And then one might be at higher resolution. So this means that we also need to have some kind of higher resolution internal model and undersample it to look like each of our different observations. And then we need to consider that each of those observations has a different point spread function. So we take our internal model, we convolve it with the point spread function model for each observation in order to do our fitting. And then we need to also consider that our different observations will have different filters. So we need to consider that our galaxies might have different brightnesses and different filters, and there are different interdependencies between them. And then a transient might go off, for example. So we need to be able to have a framework that can treat that some sources are varying and some sources aren't. So you can see that there's a lot of different aspects that need to be incorporated to have some kind of flexible forward modeling framework. And the tractor was really the first one to do this. This is the landing page if you go to the tractor, which is definitely my favorite landing page for any code that I've ever used. And what they demonstrated with the tractor is that these kinds of multi-survey forward modeling codes can be run at scale. They did this for the legacy surveys in preparation for DESI, where the goal was to have really accurate galaxy catalogs for photometric redshifts for target selection for the DESI survey. So they really showed that you can do this kind of multi-survey modeling. However, in this new regime with Rubin, which is really deep, and with Euclid, which has these really high resolutions, which really show how complicated galaxy shapes are, we needed to address a few new challenges for these new surveys. In particular, the complex galaxy shapes that we see in these high-resolution space-based images require non-parametric morphology models. Doing something like a Sircich profile won't really cut it for many of these complex shapes that we're seeing, so it makes sense to have a non-parametric approach. But then when we have these very blended, crowded fields, we need to, and low signal to noise, very faint background galaxies that we need to treat accurately, we need to have machine learning priors for stable fitting in order to help constrain the problem as we do this multi-degenerate deblending. And we also, given the source densities and just the data volume that we're dealing with, we wanted this to be GPU compatible so that we could speed it up with GPUs when possible. So it was written in JAX. And then we needed to consider the time domain aspect. We needed to be able to have single exposures and be able to forward model transients across the exposures as well. So this motivated the development of Scarlet2, which implemented the ability to have non-parametric galaxy morphology models. So we're not assuming like a Sircich profile, for example. Our internal model of galaxy shapes is an image of the galaxy. And then it has score-based neural networks that help to stabilize the fitting. And these are trained on real images of galaxies. So that knowledge is incorporated into the fitting process. It's written in JAX for GPU compatibility, and it has transient and variable source models. And you can see the documentation on the page here. And just a quick note on how the priors with score-based neural networks are applied. We have, for example, a neural network that is trained on images of galaxies. Maybe they're LSST-like images, maybe they're HST resolution images. And this is a diffusion model that is able to create images that look like galaxies from noise. And here are some examples of sort of the priors developed by Matt Sampson, and Benjamin Remby at Princeton is now developing a high resolution prior. And what it does is when you're fitting for the galaxies in a particular field, you have a term that is driving the gradient as you do the fitting. That is just based on how well your model describes the data. But then you have an additional term, which is determined by the prior and how well your model matches the prior. And this means that instead of applying hard constraints to help to stabilize the fitting, for example, forcing galaxies to be symmetric or have positive flux or whatever it might be, Instead, the prior helps to guide the fitter to have realistic galaxy shapes based on what it knows looks like a real galaxy. So here's an example where we have some artifact that does not look like a galaxy that the prior has seen. So the term that the prior adds is very strong, where we have these features to guide it towards realistic galaxy shapes. And we, of course, have this feature to model transients across the images and to have static sources in the background so that you can use these constraints and extract a light curves during your fitting. So just to summarize, before I move on to why we needed LINCC, so the Scarlet2 framework ended up being this code that allows you to do your forward modeling across imaging datasets from multiple surveys. You could, get posteriors with a sampler in order to really understand parameters of interest. You could produce high-quality galaxy morphology models and flux catalogs. And you could use it for various time domain science cases, so that you could generate light curves as well as host galaxy models, for example. So where does LINCC come in? So with LINCC, what we really needed to do is that we had this code that we were building for large-scale survey processing pipelines, and we were regularly having users come to us and trying to run it on particular images, sometimes Roman, sometimes Roman simulations, sometimes JDOST images, sometimes Zwicky transient facility images. And for a range of science cases, I've listed some of them here. We had people trying to extract supernova host galaxy models. We had people trying to run it on IFU data. We had people trying to see if their tidal disruption events were offset from their hosts. We had people trying to model strongly lensed systems. And in each of these cases, it was quite difficult for users to set up this complex framework where they had to have a very detailed understanding of their observations. They needed to have good models of the point spread functions. They needed to have good weight maps. They needed to understand how good their astrometry was. They needed to make sure their images all had the same 0 points across multiple epochs, for example. And then they needed to set up the problem. They needed to identify what is the best way to model the galaxies in my field? What is the best model to use for those galaxies? Do I want to enable transients? Do I want to apply these constraints? And there were just many ways that with this complex framework where you need to forward model, there were many ways that they could go wrong. If your point spread function model was a bit off, your fitting would not work well, and it might be very hard to identify why. Or maybe it was just hard to even tackle this problem of how do I set up this forward modeling framework for my particular science case to get out the models that I need. So what we really needed was expertise on code usability. How do we help people tackle this difficult code for their particular science case? So there were a number of different ways that the LINCC team addressed this. So the first one was building a questionnaire that was interactive and helped the users basically explain their problem, explain what kind of data they have and what they're trying to get out of the code. And then it would react to those responses with this questionnaire and build example snippets in order to show a rough sketch of how you would actually, what your code would look like for your science case. So just here, I've sort of gone through just an example of what this sort of looks like. So all you need to do is import the Scarlet2 questionnaire and start answering these questions. And it has this really nice interface. So you can say, okay, first of all, do you have one image or do you have multiple images? If you click on, say, multiple images, it would then go into the next question. Do you have transients or are you just modeling static galaxies? Are your images at the same resolution or at different resolutions? And as you answer these questions, it would provide information about how you should set up the problem and build the code as you go. So here, for example, we've just gone through the first few steps of setting up an observation object that takes in the observation data, takes in the weights, takes the point spread function, the WCS, the channels, and this will look different depending on whether you're modeling images of the same resolution, whether you have many observations or just one. And so the questionnaire will show you the example that you need for what data you have. And then as you go on, you need to start specifying things like, do I already have a source catalog, or do I need to, find the positions of the sources? Do I want to use parametric galaxy models, or do I want to use the machine learning prior? And as you can see, as we keep going on, there are many questions that you can answer and explanations that need to be provided along the way. And then over time, the questionnaire will build the snippets that you need. And then the users can pretty much sort of edit in the snippets, to make sure that their particular data can be read in, and, to say where to initialize the sources and things like that, for example. But what it means is that they already have the pieces that they need, so that they can, modify the code to read in their data, to understand the outputs. But at least it's all been set up in a way that they know what's available for their science case. And the questionnaire also has a way to take feedback. So at the end, there's a feedback form. So if it turns out that there's some new science case that we don't know about, then we can hopefully get that feedback and add features to the questionnaire that help to set up Scarlet2 for that new problem that we haven't encountered before. The LINCC team not only built this interactive questionnaire, but they made it in a way that it's very flexible, so that we can add things to it. If we have these new aspects to the questionnaire, it's really nice. So it stores the information as you go, because the way you go through this tree and answer the questions will have knock-on effects for code further down the line. So it can store previous answers in order to provide the right example code at the end. It can be saved and reloaded if someone wants to go back to where they were and try something different. And as I mentioned, it links to this feedback form so that we can, help to modify it over time and add things to it if we think we need to do it. And there's a developer guide that's part of the Scarlet2 documentation, which is great. So that was one thing. So now Scarlet2 users can build custom code for their science case using this interactive questionnaire. One other feature that the LINCC team added was input and output validation. So this was quite challenging. If you have users that, aren't fully familiar with all of their survey data products, maybe they're not sure how to generate a weight map for their image. Maybe they don't know if their point spread function model is good or not. So it really made sense to have a suite of tests that both test the observation properties that are going into the code, and to test if the models coming out are actually high enough quality or if there's room for improvement. So just to show an example of this, here is what we have in the tutorial. Users will put in, for example, their point spread function model for these different observations. And just to give one example, if your point spread function model is slightly off center, when you're rendering your model to look like your observations, things will go wrong in the fitting. So for the observation validation suite that the LINCC team built, it will test things like, do your weights make sense? Are they positive? Are they finite? Do they have the right shape? Does the channel information that you put in make sense? Is your point spread function model the right shape, and is it well centered, for example? So if users have just put in the wrong information about characterizing their observations, that can very quickly be identified before they go way down the line of trying to fit their data with which is poorly specified. So at least that can be caught early and fixed for the users. The next step was to have a validation suite for initialization of the problem. So here is an example where you might have too small of a box to model extended galaxies. So this means that there's all this excess flux that is not going to be modeled. And no matter how much you tweak your step sizes or whatever, your model is never going to be good enough because you've already misspecified the size of the galaxies. So this is one example where you want to pick this up early and fix that up. So the validation will now test your initializations and see, there's excess flux around the box or something, and pick up that your input, your initializations need some tweaking before you go any further. And then finally, once you've actually run Scarlet2 and it's done the multi-resolution fitting, you then want to see if there's room for improvement. So here's an example of a possible output of once you've run the fitting. You've got your observation, you've got your internal model, what it looks like when it's rendered to look like the observation and the residual. And then for each source, you can extract what the morphology and the spectrum looks like across your channels. And then what the validation code does, it will check that the model fits are reasonable, that the chi-squared and the box and near the border all look reasonable, so that if it turns out that by running Scarlet2 for longer, by tweaking your step sizes or something like that, you can do a better job, you can identify pretty quickly that the models are not as good as they could be. So one of the similar things, similar to the questionnaire, it's possible that over time we'll think of new validation tests, for example. So what the Link team did was to make sure that there's flexibility to add in new tests and things like that. So there is also a nice developer guide on the Scarlet2 documentation that helps to, I think I have the wrong screenshot here, but it helps to explain how to add in new validation tests over time, which is really nice. One of the other challenges that we made progress on with the Link team was the performance. So we were finding that Scarlet2 was taking too long once you were putting in hundreds of images. You might be modeling a transient across hundreds of epochs, for example. So what they did was look at how where the slowdowns were happening. This turned out to be very complicated. So I have Max's very elaborate characterization of where all the time was going in various aspects of the code here. And it turned out that this was a very hard to track down issue related to JAX and Equinox. And we were able to identify a cache missing problem that was really slowing down the code. And it was really great to know where this was. And now it's all running much faster, which is great. Just to zoom in on this very big image. And then the last thing that we were able to really help with over this project was looking at how we can get Scarlet2 to be easily usable on the Rubin Science Platform. So we really want people to be able to read in the Rubin data products on the Rubin Science Platform and run Scarlet2 on it and incorporate other imaging from other surveys if needed. So we now have a nice suite of functions that help us to read in Rubin data products so that they can be incorporated into Scarlet2, and some example notebooks on how to run Scarlet2 on the Rubin Science Platform. And here are some examples of that happening. So we have our single exposures from Rubin, as well as some nice coads, and the Scarlet2 models and on the left, and the residuals. So we have all of these nice examples for when people want to run Scarlet2 on real Rubin data over the next few months. So with all of these different features, we're now in a much better situation when we have users come to us with a different data set, a different science case, because they can use this interactive questionnaire to help them see how to structure their code and what kind of features make sense for their science case. They can test their observation inputs and see whether their initializations and the models coming out can be improved. It's running faster, and they can easily incorporate it into the Rubin Science Platform. So we've been super happy to be able to have all of these features, because previously it was definitely hard for users to come in and get started with Scarlet2. And I really think everything that the Link team has done has helped a lot. So I guess in the last bit of time, I just want to talk a bit about some of the preliminary science that is being done with Scarlet2 in its improved version. So one of the things we're working on is the Euclid Rubin derived data products, where we're doing this joint processing of Rubin and Euclid imaging. So in the near term, we've got these example Jupyter notebooks that show how you can model Rubin and Euclid images for particular science cases. And we're applying the code to supernovae and variable AGN in some of the early Rubin fields that overlap with the Euclid public data. And in the longer term, we want to use this to make joint galaxy catalogs across both of the surveys, and to also be able to have light curves of transients and host galaxy properties across the surveys as well. And here are just some examples of cutouts of this is a supernova host galaxy that was in Euclid and Rubin. And for the Lucia-Schmidt Southern Survey, which is this new time domain survey starting up now, we're hoping to be able to use Scarlet2 to make joint transient light curves across LS4, Rubin, and Euclid, as well as host galaxy models, measure spatial offsets, and have them appear on Sky Portal, which is where LS4 users are looking at all of the transients that come through the survey. So we're really excited for Scarlet2 to be able to provide all of this information about transients and host galaxies of interest. And then we've been applying it to various science cases. So we've been looking at strongly lensed supernovae. Here's an example of a simulation that this is a strongly lensed system where we have 4 different images of the same supernova in the background after it's been lensed. And you can see it's well resolved in Euclid, marginally resolved in LSST images in the middle, and unresolved in LS4. And we're able to use Scarlet2 to extract light curves and galaxy models across the data sets, which is really useful for time delay cosmography. We're using it to do decomposition of active galactic nuclei and their host galaxies in order to study populations of variable AGN that Rubin will detect. And we're hoping to sort of look at the relationship between black hole masses and host galaxy masses across the mass regime, particularly in low masses. So by using the high resolution Euclid imaging, we can do a better job of deblending AGN and hosts to this end. And for this interesting question about looking for massive black holes that are wandering outside their galaxy nuclei, we've been using Scarlet2 to identify candidates for these in surveys like Pan-STARRS, as well as in ZTF, where here we have an image of the first optically discovered tidal disruption event, where a star has been disrupted by a massive black hole. And this was offset from its host galaxy, and it really was not obvious in ZTF images. You needed to use something like Scarlet2 to really see that it was not a nuclear transient. And then with HST follow-up, they were able to see that it was, in fact, from a wandering black hole and not from a black hole that was in the galaxy nucleus. So these are just some examples of things that we're looking forward to running Scarlet2 on its scale over the next few years. And I think as we have more and more users kind of coming in with their supernovae, their tidal disruption events, with their, JWST image or whatever it might be, I think what the LINCC team has done will really help them be able to run Scarlet2 for their particular science question, for their particular imaging data, in a way that's much more accessible for people who have not spent the last few years developing this code. So we're really happy that they'll have access to all of these features to help them streamline this process. So that's actually all I had. Happily take any questions. Yeah, thanks a lot for listening.
Awesome, great. Thank you very much, Charlotte. Appreciate that very much. I see that Nevin has a hand up, but I just want to quickly remind folks that you can ask questions here in Slack, raising your hand, or via the chat here in Slack, or through the hashtag LINCCTechTalks Slack channel on the Discovery Alliance Slack. Go ahead, Nevin.
Hi, Charlotte. Great to see you again. Can you talk a little bit more about maybe, computational requirements? So like Rubin Science Platform obviously doesn't have that much memory. How do you interact with that? And maybe like how will this Rubin Euclid joint processing work? Is that like theoretically new? Like what are the computational resources that you need?
Yeah, definitely. It's a good question. So at the moment, we kind of see the way Scarlet2 will be run for joint processing along 2 prongs. The first is for users who have a particular object, a particular galaxy or transient, and that is very doable to do on the Rubin Science Platform. You use the cutout service. You can warp the images to be pre-resampled if that helps you. For example, that's in the example notebooks. So in that regime, I think it is very straightforward now with the speed ups that we've had recently to run it on the Rubin Science Platform. So for custom science cases, that's how we hope it can be done. But for this larger scale joint processing where we want to model, every galaxy that's in Rubin and Euclid, produce joint catalogs, then the computational costs do become more substantial. especially because of this rendering operation. So once you have these multi-resolution data sets and you have your internal model that's constantly being rendered to look like different observations, that's where most of the compute time goes. That is currently being run on a smaller, on a test scale at NCSA at Illinois for now. And for these Euclid Rubin derived data products, we have kind of split them into different tiers. So there's a white paper by LINCC from 2018 that kind of describes the original ideas for this, but we have a simpler tier which uses existing LSST pipeline code to do photometry without this full joint pixel processing. And then the kind of final tier, which is a little bit further down the road in probably a few years' time, involves this full joint pixel processing with Scarlet2. So that's still a work in progress for scaling it up at this level of doing full joint pixel modeling. But in the meantime, there will be earlier releases that use existing LSST pipeline infrastructure so that it can be run using the existing infrastructure, which is much faster.
Colin, if I can ask maybe one more, would that be?
Yeah, sure, go for it.
Yeah. On Rubin Science Platform, how does at the moment do you like pip install Scarlet2? Like a user would need to do that? Do you have plans or
yeah, that's right.
conversations, or what would you need to make it part of the stack or things?
Right. Yeah. So we've had some discussions about this recently, and at the moment, so Scarlet1, which was the precursor to Scarlet2, is already part of the Rubin pipeline. It does the deblending. So there are deblend tasks within the Rubin pipeline that run Scarlet1. So at the moment, Scarlet2 is not part of the Rubin stack. Thankfully, if an individual user comes in and wants to run Rubin data, you do indeed just pip install Scarlet2. You can look at our example Jupyter notebooks that we're hosting ourselves to see how to, pull your LSST cutouts, for example, read them into a format that Scarlet2 understands, and then go from there. So at the moment, it is separate. In the long run, if it turns out that it does make sense to incorporate Scarlet2 into the stack, whether that's for joint pixel processing or for some other reason, then that would be great. But yeah, that's not happening in the immediate future.
Awesome, great question. I'm going to take the host privilege and ask a question myself, which is, I'm a solar system science person, and I've come to know Scarlet a lot since working on the 3i Atlas interstellar object paper. And I have a whole new appreciation for it, but I'm just curious what kind of applications you can think of with Scarlet. Is Scarlet2 going to be used for a solar system? I know I went to a deep learning workshop a few years ago, and it's like someone broke my heart later and said, oh yeah, they're getting rid of the solar system objects, right? But in terms of either preserving or removing the solar system objects, you must have done something with that.
Right. So it's interesting because this was really motivated initially by cosmological applications, getting good, very nice galaxy models for that. So it's not something that we've been doing a lot of testing on. But having said that, we're really hoping that by having this multi-resolution framework, we really want it to be useful for crowded fields. So I think even though we haven't really been testing on it, I think there is a lot of opportunity for it to help with modeling crowded fields where your high resolution space-based image is really telling you how many sources there are and where they are. So I think there is a lot of potential there. We probably just need to talk to you all a bit more about how we can where it would help and show some examples in those fields of how you would run it.
Awesome, yeah, that would be great. Looks like, is that Kostya in there? Who I think needs to unmute here.
Myself.
There we go.
Sorry. Hey, very interesting, thank you. I also was wondering about crowded fields, like Milky Way crowded fields, where you have a lot of stars. But Colin already asked about crowded fields, so I'll ask about alerts. So do you think that it's possible to use it for alerts, or like for LSST alerts, or stamps are too small and you cannot do it? Or maybe like using alerts and using reference images from the latest data release or something like that. So yeah.
Mm-hmm. Yeah, so my perspective on this, which is definitely might change over time as we have more GPUs and try get more used to running these things at scale, is that from the point of view of alerts, I think for now, at least, it always makes more sense to just always rely on difference imaging for them. I think, scene modeling has these, it's a lot more computationally expensive. You need to make sure your background models are accurate. And for this question of, do you initialize sources as transient or not? So it's not obvious necessarily how you would do that. With the current framework, you'll need to add in that capability to actually detect whether something is transient or not. At the moment, we're from the outset specifying whether something is transient or static. So I think the typical mode of operations will be, alerts should come from difference imaging. But then if for particular objects where we can get more out of the scene modeling, especially for a multi-survey point of view, once you have your alert, you can then go back, run Scarlet2 on your data sets of interest, get a better characterization of the host, maybe create a multi-survey light curve where you don't have to worry about your reference imaging across different surveys causing any issues, and then just use it for more detailed characterization. It could also be using the sampler to get posteriors over transient position or something like that. So I think where this does fit in is more in the characterization step rather than the detection step. But that is mostly driven by the fact that this is much more computationally expensive than difference imaging. So it's hard to be optimal for detection and speedy enough for detection. But yeah, things might change. So.
Thank you. Yeah, absolutely. I meant characterization. So I meant from like Broker says, and I'm like a little bit worried about that stamps are pretty small. So they're like few arc seconds, right? And could we do anything with this like size of the stamps?
I see what you mean. So for the cutout sizes are
Sort of. That's cutout stamps is like
right. Yeah, I mean, I guess like in the way that I'm kind of running things now, I will go back and make my own stamps. Like I'll go on the Rubin Science Platform and make cutouts of the right size to help with the modeling and things like that. So it is usually done when you have full access to the imaging data and all of the data products in order to make your forward model accurate and have everything that you need.
Thank you.
Great question. I'm going to ask another question just because I can. And that is, you mentioned the GPU usage, and there's been a lot of discussion that maybe the RSP doesn't have GPUs right now. So in terms of GPUs and Scarlet2, would you say that it's sort of mandatory for training, optional for inference, or practically required for both? What would you say there?
Yeah, so it's definitely not required. So with JAX, you can either run it on CPUs or GPUs, and the speed up is of order 5 times when you're running it on GPUs, and it depends a lot on whether you're modeling large images with just a few epochs versus smaller cutouts with many epochs. But in general, I think for running the full joint pixel processing of Rubin and Euclid, it would definitely make sense to do that on GPUs. But it certainly, runs fine on CPUs. It's still fast, and it's certainly an option. I think of course, it would be nice to get that 5 times speed up when you can, but not necessary. Yeah.
Right, but it's not like 1,000 times difference.
Right. Yeah, and I will say, like, there is plenty of opportunity here for further speed up. We've just been mostly focusing on the capabilities and have often been testing it on CPUs at the moment, but that will change.
Great. Well, that's definitely what we have available. Any other last questions here? Okay, well, I'm going to take that as a no, and wish to thank our speaker again. Thank you, Charlotte. And thanks to everyone for attending the Link Tech Talk series today. Our next Tech Talk is scheduled for November 13th, 2025. But in the interim, you can join the LSST Discovery Alliance # Link Tech Talk Slack channel and the link, that's LINCC, at lists.lsst.org mailing list for more information and future announcements. There is more information, including links to the Rubin Community Forum and a calendar at our LSST Discovery Alliance website. That's for Link Frameworks and Link Tech Talks. Link Frameworks is also holding office hours every Thursday at 10 a.m. Pacific, except when it conflicts with this talk. And if you have an idea for a tech talk, we would love to hear from you. Please do reach out to us via the LSST Discovery Alliance Slack or via email. which are listed on the Tech Talk webpage. And we'll be posting this video on YouTube when we can. And with that, we thank our speaker again and wish everyone have a great rest of your day or night. Thank you very much.
Thank you.